This video describes the method of the mean bond enthalpies to calculate the enthalpy of chemical reactions. And it also works out a numerical problem to illustrate the method. Alright, so in the last video we have seen how to measure experimentally the enthalpy of chemical reactions. What we ask now is whether there are techniques that we can use computationally, right, so with pencil and paper, that would allow us to determine the enthalpy of a chemical reaction without ever setting foot in the laboratory. And there's actually three ways that we can do that, and this is just the first of one, the mean bond enthalpies method. And then we will also see Hess law and also the method of the enthalpies of formation. Now this method right here is the simplest one and the most inaccurate one, right? So this is really not used at all, but we're going to just describe it because it illustrates a very important point about the energetics of chemical reactions, and that is the energy involved in breaking and forming bonds. Okay, so here's kind of the idea of the method. The idea is that in a chemical reaction you can envision that as a rearrangement of bonds, right? So if you have an idea of what is the energy that it takes to break a bond and what is the energy that is released to form a bond, or when a bond forms, then you can actually get a good understanding for what is the enthalpy of the reaction. Okay, let's talk about this simply by thinking about the dissociation of water in the gas phase into hydroxide and a hydrogen atom. Alright, so notice that what you're doing here is you're taking a water molecule and just breaking off one bond. Now, here's a key point that a lot of people get wrong. Breaking bonds actually takes energy, it costs energy, because what you're doing is you're actually breaking the interaction of the two electrons that are intervening in that covalent bond with the protons in the nucleus, right? So the idea is that you're breaking that electrostatic attraction that is very favorable, and that costs a lot of energy. So this is going to be a positive reaction enthalpy. It's going to have a positive reaction enthalpy which is known, right? So this delta RH M happens to be plus 492 kilojoules per mole. It's a really strong bond. Okay, so that is something that it's important. Now we can think about the reverse reaction, right? So we can say, well, let's think about the reaction in which we have hydroxide in the gas phase and a proton, and the reaction is going to be that in which you form water, right? So the idea here is that the only thing that is taking place in this reaction is the formation of a bond, and this should release energy because the bond is forming the bond is much more stable than those two electrons that are involved in the bond just being separated and not interacting with each other, right? So because enthalpy is a state function, and the only thing that we've done here is just simply change the initial and the final state, the value of the reaction enthalpy will be exactly the same, but with opposite sign. Okay, minus 492 kilojoules per mole. Forming this bond will release energy, and breaking the bond requires energy. Alright, so it turns out that we actually have been able to tabulate bond energies for a variety of reactions. Then you can look at an overall chemical reaction and simply tally up the number of bonds that are broken and then the number of more bonds that are formed. Simply take the difference between those values, and that should be a good indicator of the reaction enthalpy. And it really is. Alright, so again, the equation to use here would be that the enthalpy of a reaction, alright, is going to be the enthalpy that you have to supply in order to break the bonds, which I can simply write as broken, HM, minus the enthalpy that is released when you form the bonds. So that will be the enthalpy of the formed bonds. All right, so there's tables with the enthalpies of bonds, average enthalpies of bonds, and then you simply have to take them and just add up the enthalpies of the bonds that are broken. That will be positive. Then add up the enthalpies of the bonds that are formed, then change the sign, and that is going to give you the overall reaction enthalpy. right? So here's a key point. If the bonds that you're forming are stronger than the bonds that you're breaking, then the reaction will be exothermic. It will overall release energy. Conversely, if the bonds that you're forming are weaker than the bonds that you need to break, then you will need to supply energy as heat overall to the reaction, and it will be endothermic. All right, so let's just run a simple example, and then we'll just wrap up. Okay, so the reaction that we're going to be looking at here is the combustion of methane with oxygen in the gas phase, which is going to give, involve 2 oxygen molecules, and is going to generate 1 CO2 molecule, and then is going to also generate 2 water molecules. And we're running this reaction in the gas phase at conditions such that all of the species, the phases that are stable, are the gases. All right, so let's just simply tally out how many broken bonds are and how many bonds we formed, and the balance of those enthalpies will just be what we need. All right, so broken bonds. Let's see. In broken bonds, we have that in reagents that you draw here, the Lewis dot structures of these molecules, you will have that there are 4 CH bonds that are broken, and then in O2 you have that is a double bond, right? So notice that you will have 2 double bonds between oxygen and oxygen, right? So that is the enthalpy of the bonds broken, and from here we just have to subtract the enthalpies of the bonds that are formed. Okay, and the bonds that are formed, when you think about CO2, right, there are 2 CO double bonds, and then here you are forming water, you will have that. So there's 2 OH bonds per water, you have 2 water molecules, so that will be 4 OH bonds. Okay, so now you go to the tables and just look at what these values for the enthalpies of these bonds are, and then you'll solve the problem, right? So you go to the tables, and it happens that the enthalpy of CH bonds happens to be 412 kilojoules per mole, so that would be 4 times 412 kilojoules per mole. And then you look at the enthalpy of that double OO bond, and that enthalpy is 497 kilojoules per mole. And then you subtract the energy or the enthalpy of the bonds that are formed, right? So that is going to release energy from now on. And then you have 2 CO bonds that are worth 743 kilojoules per mole. These are really strong bonds. And then 4 water OH bonds, which are worth 462 kJ per mole. Okay, and actually 63 kJ per mole. And that means that when the dust settles, you do all that in your calculation. This should be an exothermic reaction. You're burning methane, right? So that's natural gas, essentially. So this should be exothermic. And it is. The prediction is that this is going to be minus 696 kilojoules per mole. Okay, so notice how simple the method is to use. You simply have to just, again, tally up all of the formed and broken bonds, and then add them or subtract them appropriately. There are great caveats to this method, and one of them is that first, the numbers that appear in table are average. So for example, at the start of this video, we looked how breaking the OH bond in water was worth 492 kilojoules per mole. However, the enthalpy that we have used right here is 463 kilojoules per mole, and that's because what you have in tables you will see OH bond. But that's simply an average of a variety of OH bonds that people have measured. That would include that in water, but also the one in methanol, the one in ethanol, and so forth. So what you really get is an average and not the specific bond that you're looking for, and that's why this method is really inaccurate, right? So it only gives you an indication, not true accuracy. The second caveat is that generally the values that you have in the table are for gas phase species, right? So if you were to run this reaction under room temperature conditions and of temperature and 1 bar of pressure, then water would be a liquid. And what that would mean is that the calculations would not be as simple, because then you would need to figure out how to vaporize that watery gas into the liquid water into the gas before you can do this, because all of those enthalpies or the mean bond enthalpies that you have in tables are for the gas phase. So generally what this means is that this method is not used in reality to calculate any reaction enthalpy to sufficient accuracy. However, it's a really good indication for, very easy to use as well, for whether the reaction should be positive or negative. And it also speaks to the value of thinking about the energy in a chemical reaction as simply having to do with whether you're forming stronger bonds that you're breaking or the other way around. In the next videos, we're going to see more accurate and useful methods, which are the Hess law and then the method of the enthalpy self-formation.